Hello, everyone, and welcome to today's lesson on 8.1 Work Permits and Energy Isolation. Compared with maintenance in other industries, the maintenance of chemical production facilities is characterized by high complexity and significant hazards. Implementing a work permit system and applying energy isolation methods are effective means to strengthen management of maintenance operations and control hazardous energy, and are also crucial measures to prevent maintenance accidents. Let's understand this with a case study in the early morning of December 3rd, 1984. A pesticide plant owned by Union Carbide in Bhopal, India, experienced a cyanide leak, which resulted in severe consequences, a human tragedy that directly caused 25,000 deaths, indirectly 550,000 deaths, and left over 20,000 people permanently disabled. Even today, the cancer rate and child mortality rate among local residents remain far higher than those in other Indian cities because of this disaster. Let's review the sequence of events in the accident. On the afternoon of December 2nd, 1984, during routine maintenance, personnel attempted to clean a clogged filter on the process pipeline. Before using water to backflush the filter, they simply closed the valve and proceeded to clean the filter. Due to corrosion, the valve developed an internal leak, and during the backflushing process, 1 to 2 tons of high-pressure flushing water passed through the valve and entered the MIC storage tank. MIC is methyl isocyanate, and at a certain temperature, MIC undergoes a strongly exothermic reaction with water under the catalysis of iron ions. When water entered the tank, it reacted exothermically with the MIC present, causing the temperature and pressure inside the tank to rise. The tank became overpressurized. The safety valve lifted and MIC was released into the atmosphere. This was the most direct cause of the accident, which shows that valve isolation was unreliable. If maintenance personnel had followed standard operating procedures, by closing the valve on the process pipeline and installing a blind flange at the isolation point, and by applying for and obtaining a work permit before starting the work, this disaster might have been prevented. Let us first study work permits. The work permit system is a safety management system that requires approval and authorization before conducting non-routine or hazardous work to ensure safety during the work. Participation in non-routine or hazardous work must adhere to the work permit system. For instance, maintenance tasks that are not part of the routine maintenance schedule and lack procedural guidance, the 8 major special operations and maintenance of equipment with high safety risks, all require adherence to the work permit system. The work permit process is divided into 4 stages: application, approval, execution, and closure. Before work begins, the applicant must fully verify the work content and procedures, organize the relevant work safety risk assessment, and determine the necessary safety control measures. Then, in accordance with the requirements, complete a safety work permit and submit the work permit application to the approving authority. The approving authority is responsible for reviewing and approving the work permit. Typically, various management personnel authorized by the company. Before work begins, the workers must fully verify all safety conditions and strictly implement all requirements outlined in the safety work permit and work safety analysis. After work is completed, the applicant and the approver confirm and sign off, and the work permit is closed. When there is a change in work content or an expansion of the work scope, the work permit should be immediately withdrawn, marked as void on the permit, and on-site work must be halted. If work needs to continue, a new safety work permit must be issued. Work permits may be extended, but extensions are only applicable if the safety measures remain effective and the work conditions do not change, with the applicant, the approver, and relevant parties re-inspecting the work area. The second topic is energy isolation. In chemical production processes, we encounter various types of energy. For example, some operating equipment generates mechanical energy. Electrically energized equipment contains electrical energy, and chemicals possess chemical energy, among others. When the energy contained in process materials or equipment could cause injury to personnel or property damage, we refer to it as hazardous energy. The unintended release of hazardous energy, along with the resulting electric shocks, fires, explosions, poisoning, corrosion, and burns, is one of the major causes of work-related accidents. To prevent accidents, we need to control the source that causes accidents, and this source is energy, in other words, the hazard. If no energy is released, no accident will occur. Therefore, it is imperative to implement energy isolation. Energy isolation means positioning valves, electrical switches, and energy storing components in appropriate locations or with the aid of specific facilities so that equipment cannot operate or energy cannot be released under normal circumstances. There are two methods of energy isolation: mechanical isolation and electrical isolation. Mechanical isolation is used to isolate various forms of energy in materials, which is also referred to as process system isolation. Electrical isolation is used to isolate electrical energy. Let us first examine the process system isolation method. The first is valve isolation, which includes double valve isolation. Valves closed on both sides with venting in the middle, and single valve isolation, generally for low-risk scenarios with no inlet conditions. Valve isolation is used. However, due to corrosion, valves may develop internal leaks, so valve isolation is unreliable. Complete isolation is generally applicable in high-risk areas. For example, at the connections between equipment and pipelines during purging, or when ensuring gas-tight conditions, or in high-temperature hazardous work areas. N8 shaped blind plate can be rotated, or the pipeline can be dismantled to completely blind the open end, or a blinking plate can be inserted between flanges. Electrical isolation is performed by qualified personnel, disconnecting all main power sources and verifying the effectiveness of the electrical isolation. Throughout the entire electrical isolation process, power shutdown and power restoration are involved. First comes power shutdown. The electrical department contacts for shutdown. The power department responds by checking that the circuit can be shut down, performing the shutdown operation, hanging a "Do Not Reclose Personnel Working" sign, and filling out a power outage notification form. After maintenance work is completed, the electrical department contacts for power restoration. The power department responds by verifying that the circuit can be re-energized and remotely measures insulation to at least 1 megohm, generally for motors below 500 volts. An insulation resistance of over 0.5 megohm is considered acceptable. Removing warning signs from the circuit components and then performing the power restoration operation, The valves used for isolation and the power sources for electrical isolation must be secured or locked out so that they cannot be operated. These include valve locks, such as disc locks, ball valve locks, and chain locks, as well as certain electrical locks. The locking devices should bear traceable tags, indicating the reason why the valve has been locked out. Lockout must always be accompanied by tagging. The purpose of implementing lockout and tagout is to standardize the most basic isolation and protective measures required for production equipment to prevent damage to personnel, the environment, or equipment due to carelessness or improper operation, thus ensuring the effectiveness of the isolation. When maintenance is required for faulty equipment, typically, process personnel will perform energy isolation and apply lockout and tagout, then test the effectiveness of the isolation, and once confirmed, the process personnel hand over the equipment. Maintenance personnel then apply their own lockout and tagout and test the isolation effectiveness. This constitutes the lockout and tagout procedure. Subsequently, maintenance personnel perform the repair work, and once the repair work is confirmed to be completed, the maintenance personnel remove their locks and tags and notify the process personnel that maintenance is complete. Then the process personnel inspect and accept the equipment, and once it is acceptable, the process personnel remove their lockout tagout, which is the procedure for removing lockout and tagout. Now the energy isolation operation procedure is as follows. Step 1. Preparation. Notify the relevant personnel and use a job safety analysis to identify all sources of hazardous energy: mechanical energy, electrical energy, chemical energy, thermal energy, etc. Apply for an equipment maintenance work permit. Step 2. Isolation. For the identified hazardous energies, clearly designate the isolation points and types and implement a series of measures, including power disconnection, valve closure, blind plate removal, depressurization, cleaning, and purging. Step 3. Lockout and tagout. Select appropriate locks and tags according to the isolation checklist, with the tag containing the name of the person locking out, the date, the department, a brief explanation, and contact information. Step 4. Verification. After lockout and tagout, reconfirm that the hazardous energy sources have been isolated, that the power supply has been disconnected, and that all hazardous items have been removed from the site. Step 5. Testing. Attempt to start or move the equipment to ensure that the hazardous energy and materials are completely controlled. Step 6. Execute the work. Notify the maintenance department to perform equipment repair and maintenance. Step 7. Restoration. After work is completed, reactivate the safety devices, check and account for all personnel and tools. Remove the lockout and tagout devices and notify the relevant personnel to restore the equipment's power supply. This is the energy isolation operation procedure. Next, we will watch a video to learn the standard procedure for implementing energy isolation and the related safety precautions. With the advancement of human technology, mechanical energy, pressure energy, light energy, thermal energy, chemical energy, electrical energy, and radiation energy have all been harnessed for use. While these forms of energy, though beneficial to humanity, have also brought threats and disasters. Before various maintenance and repair operations, the failure to isolate hazardous energy has resulted in injuries or fatalities, such as chemical burns, poisoning and asphyxiation, fires and explosions, mechanical injuries, and electrocution. Exposing issues within the companies responsible for such maintenance work, including deficiencies in management, systems for energy isolation, unclear risk identification, poor safety awareness, insufficient skills training, and incomplete protective equipment. In order to learn from these accidents and prevent future occurrences, we use the example of handling a flange leak at the outlet of a centrifugal pump in the river water circulation system at the training base to demonstrate the standard energy isolation procedure and the associated safety precautions. First, when the field operator during inspection of the operating river water circulation system discovered that the centrifugal pump's outlet flange was leaking. Second, after reporting to the shift supervisor and following instructions, the operator shut down the centrifugal pump, closed the inlet and outlet valves, and drained the water from the pipelines and pump casing to create process conditions for addressing the flange leak. Third, to ensure safety during the leak tightening operation, the field operator contacted qualified electrical maintenance personnel to perform electrical energy isolation on the centrifugal pump at the production site, and then, according to regulations, filled in the power shutdown request form with the applicant's unit name, the facility name, the equipment name and its location number, the requested shutdown time, the applicant's name, and other required information. Fourth, once 2 electrical maintenance personnel arrived on site, the shutdown operator confirmed the shutdown steps on the power shutdown request form and then proceeded to the distribution room to carry out the centrifugal pump's electrical energy isolation operation. The shutdown operator ensured proper insulation protection, opened the distribution box, disconnected the air switch, closed the distribution box, and locked it. The shutdown supervisor then verified that every step was correctly executed, ensuring that the power switch positions and indicator lights confirmed a no power condition, and finally hung an energy isolation warning sign. Fifth, once confirmed, the 2 electrical maintenance personnel returned to the signing area, recorded the actual power shutdown time on the power shutdown request form, and signed off jointly. 6. The field operator then went on site to confirm that the centrifugal pump's power switch indicator lights were off and pressed the pump's momentary start or start button, and when the pump failed to start, it indicated that the electrical energy isolation was successfully completed. 7th, after the field operator completed the on-site confirmation, they returned to the signing area, recorded the confirmation time on the power shutdown request form, and signed off. 8th, next, the process moved into the defect elimination and leak tightening maintenance phase after the field operator completed and issued equipment maintenance work permit and handed it over to the maintenance worker. The maintenance worker carried out leak tightening work on the pump outlet flange, and after completing the leak tightening work, the maintenance worker returned to the signing area, recorded the completion time on the equipment maintenance work permit and signed it. Then the operator went on site to open the centrifugal pump's inlet valve to allow water into the pump, and after confirming that there was no leak at the pump outlet flange, returned to the signing area and signed off on the equipment maintenance work permit to confirm. The operator then contacted the electrical maintenance personnel again to perform the centrifugal pump power restoration operation at the production site and according to regulations, filled in the power restoration request form with the applicant's unit name, facility name, the power restoration equipment name and its location number, the requested restoration time, the applicant's name, etc. 9th, once 2 electrical maintenance personnel arrived on site, the power restoration operator confirmed the power restoration steps on the power restoration request form, then proceeded to the distribution room to perform the centrifugal pump power restoration operation. The power restoration operator ensured proper insulation protection, opened the distribution box, closed the air switch, closed the distribution box, and locked it. The power restoration supervisor then confirmed that each step was executed correctly and that the power switch positions and indicator light status indicated that power was restored, and finally removed the Beyond Energy isolation warning sign. 10th, after confirmation, the 2 electrical maintenance personnel returned to the signing area, recorded the actual power restoration time on the power restoration request form, and signed off jointly. 11th, the field operator then went on site to confirm that the power switch indicator lights had lit up in red and pressed the centrifugal pump's momentary start button, and the pump started momentarily successfully, indicating that the centrifugal pump power restoration operation was complete. 12th, after the field operator completed the on-site confirmation, they returned to the signing area, recorded the confirmation time on the power restoration request form, and signed off. 13th, finally, the field operator made, in accordance with higher level production instructions, put the centrifugal pump back into service to establish the river water circulation. Through the video demonstration, we have explained the definition of energy isolation, risk identification, work procedures, safety measures, and the responsibilities of the relevant personnel. Please commit this standardized energy isolation process to memory and apply it proficiently in your actual work so as to ensure the effective implementation of energy isolation prior to all maintenance operations. That concludes today's lesson. Thank you, everyone.